Okay. It seems that this semester there's a meta project here to make some of my old papers obsolete, right? Somebody else and now much will do. List Decoding.
Thanks. Thanks, Avi. I'm not sure it's obsolete, but we've been trying very hard. You need to tell us what result to move on to next.
Yeah.
After this one. Okay, let me just start with a really brief overview of what we're going to cover. So this talk is based on joint work with Yotam, Russell, and Tony. As Avi said, it's about local list decoding, its connections to complexity and hardness amplification, pseudorandomness, and other topics. Roughly speaking, this is part one of a two-part talk. So Yotam is giving the second half of next week. So roughly speaking, the outline for this first half of the 4-hour talk is I'm going to introduce the notion of local decoding and error correcting codes and local list decoding and what is this. In the second part, I'm going to talk a little bit about its applications in complexity and pseudorandomness and hardness amplification, and briefly in the construction of pseudorandom generators. And finally, in part 3, we're going to try to prove a baby version of sort of our new locally list decodable codes that suffice at least for some pseudorandom generator application that I'm going to show. And I guess in the following week, Yotam will give the real construction, or some version of it. Okay, so let's go ahead and get started. I want to start with an arguably practical, motivating question, which is say that I am Facebook. Maybe I work at Facebook. I don't know. Unlikely. But and I have a huge database. I have a collection of everybody's Facebook pages. And I need to store this data in some way. I'm going to represent this as a function, Boolean function for simplicity. So say I have a Boolean function f. Or I guess we'll just think of actually as a string for the moment, a string in 0, 1 to the capital N. And again, think of capital N here as huge, right? Facebook has billions of users. It's an enormous string. I'd like to store it in some way that is robust to errors. So can I encode f, restore f, encode f as a longer sort of redundant string, which I'll write is enc of f, that's in some 0, 1 to the n prime for n prime significantly longer than n. Such that it has two properties. One is that even if encf gets quite corrupted, there's somebody, I don't know, some server goes down or I lose access to some encf, I should still be able to recover my original database. I want to be able to, download, allow people to pull their Facebook pages. So can I recover f even if, let's say, a constant fraction, a small constant fraction of enc of f is adversarially corrupted? So here, the bits are flipped. There are multiple models you consider. We'll just consider sort of errors.
Anyway, there can I, because it's the option. Just that.
I'll replace can I with I can. Such that I can recover f, even if, even if some row fraction of encf is corrupted. And two, this is why I was sort of stressing that this n is so massive. If I want to just, look at my Facebook page, I don't want to have to look at the entire encoded database of all of Facebook to decode it. So is there some way that, for any index, that I can decode just the value, the bit value of f of I, reading, a highly sublinear fraction of n prime, just querying a few locations in this encoding of f. So I can decode f of I, maybe with high probability, probabilistically, just query, reading encaph in a few locations. At least, sublinearly many locations. We'll talk a little bit more about what you can sort of hope for in this type of problem.
So the decoding is assuming the encoding is not correct.
So good. No, this is saying even if a row fraction are corrupted, right?
Including I.
Including I.
Including I.
Yeah, including I.
Yeah.
Right. So I'll show you a code where this is possible in just a few minutes.
Sure.
It's saying even if encaph is row corrupted for all I still want to be able to read a few random bits of the encoding that maybe are somehow redundant. Give information about I and decode the correct value of I.
I guess my question is, why can't I then just corrupt the sublinear number of locations?
Because it's going to be randomized. So you cannot have it, very good, you cannot have a deterministic locally decodable code. For exactly this reason, I was going to say this, but I defined locally decodable codes. That's perfect. So it's a randomized algorithm. Very good. And we'll say, basically, I want to decode this with 3/4 probability, and I could just do it a bunch of times and take a majority to get a really high probability of the right answer. Okay, very good. I'll formalize this model in just a second. In fact, right now. So this, as I'm sure many of you know, is called an error correcting code. I switched to the wrong end of this. Yes. And this is called being locally decodable. Okay, so I want to actually formally define these terms for you a little bit more carefully. I guess I still have some board space here. So let's first start with one. Okay, maybe let me say, I'm sure many of you are aware that error correcting codes are useful beyond just this problem. They've become sort of a central tool in theoretical computer science. They're used in algorithms, complexity, pseudorandomness, cryptography, et cetera, et cetera, et cetera. I'll show you, a few of the examples in hardness amplification, et cetera. But they're extremely useful objects beyond just this practical question of database storage or communication. Often this is said instead in a way that Alice wants to send a message to Bob, but the message might get corrupted and Bob wants to decode the message. Okay, so let's define an error correcting code. So a mapping right, this is the encoding function. We're going to say that this is decodable from row errors, row fraction of errors. If there exists an algorithm, decode, which for now is just a function that takes in strings in the encoded world. And outputs a message with the following guarantee. For all input words W, by the way, just notationally, I'm going to try to always use W for input encoded, possibly corrupted encoded things, and F for messages, original messages. If there exists a function at a message F, which is row close, whose encoding is row close to W, so most of row fractions have been corrupted. The distance of the encoding of F and W is at most row, then the decoding should be successful, right? This should imply that the decoding of W gives me back the message. Okay, let me draw just a quick, probably everybody gets this, but it's also very nice to see pictorially. All right, so one way to think of this is I have this this original message space 0, 1 to the n, where all my messages are really close to each other in this square, and I'm embedding them into some larger space where the messages are now spread out. Right? The function maps each of these messages to something that's spread, such that if I draw a ball of radius rho, around any of these points, there should be no other points within it. I should be able to uniquely map this back to the original message. Okay. Any clarifying questions on error correcting codes? Maybe let me mention parameter-wise, the goal here often is to have n prime be as small as possible while being able to decode from as many errors as possible. This is the trade-off between people would call rate, how small n prime is, and how error tolerant the code is. This is a long-standing and very well-studied question. We won't be, there's a lot of focus on exactly what parameters you can achieve. We're going to be a little bit more coarse-grained than that. But in general, our goal will to have n prime be O of n. That we'll want only sort of a constant factor blow-up, where the constant can maybe depend on rho, but it shouldn't be, n goes to n squared or something like this. These are often called good codes that have only a constant factor blow-up. Maybe I'll just mention, I don't want to go too much into explicit constructions of good codes, but I'll just mention that if you take, just a bunch of random points in a larger space, it's pretty easy to show that they will be well separated, that we'll have this type of good code structure. Building explicit codes that have fast decoding algorithms. Right here, I've said nothing about decoding actually being computationally efficient. For these objects to be useful, probably I want a polynomial time or even your linear time algorithm for decoding. This is much harder to do, and there's a lot of research on this angle, but I'm not going to go too much into this exact part of this. Okay. Any questions before I define locally decodable codes? Maybe one question is like, what can I take rho to be information theoretically? How many errors can I build good codes that are tolerant to? I'll discuss this in a bit. The answer is about 1/4 if you want to have reasonable rate. Okay, so I basically already told you what LDCs are. So the same C notation that I'm defining above. The C is a Q query LDC, locally decodable code. Again, from say radius from rho errors. If for the same setup of W being rho close to NF, I'm not going to rewrite it. For all indices of the message, I guess I should say there exists decoding algorithm DEC, which now takes in has oracle access to W, can query the encoded potential encoded word in a few places, and it takes in an index. And the guarantee we want, right, is this probabilistic guarantee that says the probability over the internal randomness of the decoder that is equal to f of I, that I get the correct I fit, is at least, let's say, 3/4. And I can always amplify this by taking majority. And of course, this decoder should only read W, should only read the input word in Q locations. So depth. At most Q queries. Okay. I'm not going to worry too much about this, but in general, I'll mention that there's a difference between number of queries that DEC makes and the time that it runs in. There can be cases where it's really hard to compute what queries it should make. in general, the algorithms we work with are all going to be fairly efficient with running time sort of close to Q. So I'll maybe mention it briefly in a couple of places, but I'm not going to talk too much about this. But this is a challenge that shows up, and it'll show up towards the end of the talk and your Tom's talk more as well. Okay, so if there are no questions about this definition, I want to actually give an example of such a code. I mean, this seems to me like I think the first time I saw this, it was sort of surprising that you can encode information in this way that's extremely robust to errors. And it turns out you can get, you know, codes which only query O of one locations, at least for some and prime, and these are used in PCPs and various places. So the first example of this, I guess I can use this report, it's called the Hadamard code. Can people see the board over here?
Max, do random codes any interesting parameters?
That is a very good question. So you're not going to get efficiency. In terms of Q, there is, I know, an old paper of Tally, I can't remember the other author, I don't know, Avi, if you remember who it was, who showed that very sparse.
It's Madhu.
It's Madhu.
Yeah.
Who should show that really bad rate random codes do have local decoding. I believe in the higher rate regime, nothing is known. I was asking ChatGPT whether anything was known last night. So I think it's not known, and ChatGPT thinks it's not known, but who knows? I don't know if Avi, you know of any other.
They're just not.
No, we do.
Well, how many queries are you interested?
Oh, no, sorry. Right. We know that any like good code must make at least log n queries. But we'll be in sort of the high rate, high query regime. So here, I think basically nothing is known as far as.
For random codes specifically.
I don't think anything is known. I mean, I suspect you can't locally, but okay. I mean, I don't even want to say.
The distance is too large, I think already.
Let's
Like a linear code.
I see. Okay, that might be the case. I'm not sure.
So what did you say again about good codes now? That good codes require log n.
Oh, there's a result of Katz and Trevison showing that if you want to have constant rate, you have to make at least log n queries. I'll talk in a bit about sort of what is known in the higher rate regime for this type of.
Which of the assumptions there you don't assume together?
Sorry, to get.
Why is your code not, what you're going to show us is not good?
Oh, because the Hadamard code has, well, encode n into 2 to the n bits. It's going to be a massive. It's just the simplest example of.
N prime is not linear.
Yeah, n prime will be massive. Yeah, getting n prime down to linear and n, and even getting sublinear queries is pretty. I mean, Reed Muller does it, but getting below this is highly non-trivial. And in fact, for high noise, it wasn't known. This will be one of the results that we.
How does Reed Muller do it?
So we'll do all the marks first and then.
Yeah, okay, let's, I'll get to it, although I won't go into too much detail. Okay, so the Hadamard code. Right, so this will immediately answer Duran's question. It maps n to 2 to the n, so very much not a good code, but a fantastically locally decodable code, or will be. How does it do this? It maps for every, it's indexed by alpha in 0, 1 to the n, and the value of Hadamard of f at alpha is the inner product of alpha with f, right? So there are 2 to the n possible vectors, and here I'm writing down every inner product. Okay, there's an extremely simple decoder for the Hadamard code. If you just want to beat half advantage, it's only 2 queries. It turns out that exponential length is tight for 2 queries, but I won't go into this. So here's the decoder. So let's say I want to decode f of I, given my, from W. And we'll set rho to be a fourth minus epsilon. So it'll be a little bit less than 1/4 corrupted. How am I going to do this? I'm going to exploit the linearity of this code. And I'm just going to output, or I guess I'll do 2 steps. I'll pick a random vector u and 0, 1 to the n. And I'm going to output W of u plus W of u plus EI. Okay, why does this make sense? If these two were actually correct encodings of f, right, this would be the inner product of UF plus the inner product of U plus EI of f, which of course is EIF, which is the I bit of f, right? So what's the probability? U is completely random, and marginally U plus EI, because U is random, is also completely random. So the probability that both of these is correct. Sorry for the board, but probability that WU and WU plus EI compute f just by union bound is greater than half minus 2 epsilon, in which case I get the right answer. Right, so this decoder gives the right answer with probability strictly greater than 1/2. If I take a majority over maybe 1 over epsilon-ish times, I'm going to get the correct answer with 3/4 probability.
Plus.
Definitely should be half plus. Thank you. It would not work otherwise. Was that the confusion, Rahul, or could you not read the board?
Oh, no, I was just, 1 over epsilon squared, right?
Oh. Yes. Yes. 1 over epsilon squared. Sorry. Good. Thank you for catching that. Okay, so are people happy with this decoding algorithm? It's not going to show up again, but it's the simplest locally decodable code, at least that I know of. Okay, so let's take a look at the parameters of this code. We had 3 parameters we cared about, I guess. We had n prime, the block length. This was 2 to the n. So that's sort of horrifically bad. If I'm Facebook, I'm probably not going to encode into exponentially many bits. I had the query complexity, which was, let's just say it's O epsilon of 1. It's a constant, infinite of n. So that's fantastic. And then it could decode from a 4th minus epsilon errors. And it's sort of less clear whether this is the right answer in general. So I want to spend a moment briefly talking about this sort of decoding radius and what it means to try to decode beyond this 1/4 errors. Okay, so the first thing that I want to claim is that this is definitely tight for the Hadamard code. And in fact, this is not just going to be a property of the Hadamard code, it's going to be tight for any code of sufficiently small block length. Like if n prime is less than 2 to the n, it turns out there's an inherent barrier at 1/4. Let's just see it for the Hadamard code. It's not too hard to see in general, but it takes more time than I'm willing to spend on it. So consider messages f1, which is just for some string in n minus 1, 1y, and f0, which is 0y. So the encodings only differ on the first bit. My claim is that when I take the encodings, hopefully this is fairly clear, of f0 and f1, these only differ when the vector that I'm taking the inner product with are 1 on the first coordinate, right? So in particular, these differ only on half of the coordinates, right? So these are half close to each other. But then, of course, if an adversary comes in, they can flip half of those values and end up getting to the same W, whether they started at F0 or F1. Right? So, adversary at rho equals 1/4 can output W, which could have come from either of these messages. So I can't possibly uniquely decode. And this distance 1/2 thing, this is what generalizes. Turns out any good enough code can't have sort of distance, this sort of distance better than a half. It comes from the Plotkin bound. Okay, but this is sort of unsatisfying, right? Because at a quarter errors on a Boolean domain, my word W is still extremely correlated with the message F. Right? The original message F is 3/4 the time it agrees with it. So it seems like we should be able to still do something useful. I shouldn't just throw my hands up and say, okay, I can't give you, the unique message, and I'm done. So from this picture, one natural thing that I could do is say, okay, I can't tell you if it's uniquely F1 or F0, but I can promise you that it's either F1 or F0. That's still pretty useful information, right? I can try to output a small list of possible candidates and say, I know, as long as I had less than rho greater than 1/4 corruptions, here are 10 code words that it could have come from out of 8 billion. It must have been one of these 10. This is pretty useful, right? Algorithmically, it might be the case that I can just then go check these 10 solutions and pick the best one. Or even as an encoding thing, right? If 9 of them are garbage and one of them is my Facebook page, it's probably pretty easy to figure out which of these I wanted to decode. Okay, so this is a model called list decoding of Elias and Wozencraft. It's been around since the 1950s. And I'm now remembering I wanted to define it over here. Okay, great. So code C, again, 0, 1, and 1 to become prime. I'm going to call it L list decodable. From row errors. If there exists a decoding algorithm, I'll read this the next line. So now the decoding algorithm will still take in a word in 0, 1, the n prime, but now it's not going to output a single message, it's going to output a list of L messages. With the following guarantee, that for any W, this list contains inside of it all the functions F that are row correlated with W. So I'll write this as the row ball around W. And this is, all messages F such that the distance W and NCAF is less than or equal to rho. Right, and typically here we want to think about rho as sort of being beyond this 1/4 barrier. In particular, you might hope to get decoding up to a half. Right, at the point that I have half errors, I'm basically random noise. Right, if I just take any code word, I randomly flip a coin for whether I flip the bit or not. This is going to corrupt about half of the code word, and the distribution of this message is just going to be completely random noise. It's the same as if I just generated a completely random string. So at 1/2, I have no information at all, and the best thing I could do is output the entire code. Could have been essentially any message. So the goal is sort of for rho, up to half minus epsilon, our goal would sort of be, this definition is trivial based on how big L is, right? If L is as big as the code, you just output the entire code. So our goal will be to have constant list size. Typically, we'll want L to be something like polynomial on 1 over epsilon, but just some function independent of n. Again, like we want the rate to be constant, a function not depending on n. Similarly, we'll want this list size to be useful, to be as small as possible, preferably constant. Okay, maybe just, I don't think this is too hard to see, but there's also a nice geometric picture of this, right? Which is basically every ball in this space of radius rho should have less than or equal to L points in it. Instead of having a unique point that I can go to, it should be a most L. Okay, so this is list decoding. Again, turns out not only to be useful in encoding and communication, it's an extremely useful tool throughout many areas of TCS. We'll see some sort of application to complexity and pseudorandomness in a couple minutes. But I won't stand here and list all the applications of list decoding. Shashank probably knows it better anyway.
Is a random code list decoding these parameters?
Yes, good. I did want to say that. A random code should be, so you have to be a little bit careful, I think, about this list size and like how exactly the rate, how exactly n prime depends on epsilon and the list size. There's some like involved dependencies between these. But if you're willing to not get, exactly as optimal as possible, yes, a random code will satisfy these, but you won't be able to decode it. Or at least we think there shouldn't be a computationally efficient way to actually decode this. So again, we'll be interested in explicit constructions of these types of objects that have fast decoding algorithms. In fact, based on what we talked about earlier, we actually want them not to just have fast decoding algorithms, we want them to have local decoding algorithms. So that leads to the final definition of this unfortunate fiesta of definitions. Trust me, it was worse before I talked to Avi, so. Which is what it means, what does it mean to decode locally in this list model? So this will be our final definition for the moment, and then we can actually state some theorems. So C is locally list decodable. XL list decodable. I'm not going to repeat, from radius row, etc. The guarantees are going to be the same. So what can I possibly do? I have to output this list for possible code words or possible messages. So, okay, I guess the most natural thing to do is to output a list of local decoding circuits or local algorithms, such that, for any F that I want to decode, one of these local algorithms will locally compute F, will locally decode F. So I have an algorithm A that outputs a list of decoders with the guarantee that, for all W and with maybe 99, this will be a probabilistic algorithm that generates these with maybe something like 99% probability for all F that are in this, that are row correlated with W. One of these decoders will, the definition is still up here somewhere, right? Where's here? One of these decoders will satisfy this guarantee, will be a local decoder for F.
Only I should not be I. Will not become.
That is confusing. Let's do J. Yeah, so for all F, there exists some, dec J such that dec J of W locally decodes F. Just in exactly this sense. So given the index, any index with 3/4 probability, it gives me the correct thing. And it should only query, this decoder should only query W in Q places. So I should have said, Q queries. Okay, great. So now the goal is to build these objects that are extremely noise tolerant, right? Basically all the way up to completely random noise. I'm hoping to output a small list of decoding algorithms, which locally will decode, any f that is half minus epsilon correlated with my input. Okay. So then the last thing I want to do is come back to the Hadamard code and tell you that in fact this code is already locally list decodable. It's extremely good locally list decodable code, except for the fact that n prime is 2 to the n, which is terrible. But otherwise, it has fantastic parameters. I'm not going to go deeply into this because I'm realizing that I prepared 6 hours of material for a 2-hour talk.
Does it locally decode f or the jth bit of f?
Right, locally decode. No. This is the jth decoder that got output. The guarantee is that one of these algorithms, if you feed, these are algorithms that take in, indices I. So one of these DEC, when fed I, will output f of I. Does that make sense?
Yeah.
Right. So there's a list of possible messages that could be correlated here. For each of those messages, one of the decoders should compute that message.
Yeah, you have to be careful about the order quantifier. You can have a decoder that always answers 0.
Right.
And a decoder that always answers.
Right.
1.
I need the same decoder on each of the I to compute f. Right. Otherwise, this is a useless notion.
A is getting W as well.
Yeah, I guess in all of our algorithms, A will not actually use W, but it will pick a point of advice that it should start at. But you're right. I think in the general definition, A is allowed to have access to W, but we won't actually need this. Okay, so let me just briefly say now what sort of parameters do you get for the Hadamard code? This is the answer. That's actually, I think, 1 over epsilon squared, but basically you can achieve these parameters that I said over here. The reason is roughly that, f that are correlated with W correspond to a heavy Fourier coefficient. And there can be at most 1 over epsilon squared heavy Fourier coefficients. So I run some sort of local algorithm to estimate Fourier coefficients and I output the heavy f. Okay, this is called the Goldreich-Levin algorithm. It's an extremely useful old result in coding theory and learning and cryptography. Okay, it achieves these parameters. So now the question is, let's say that I don't want to have exponential blow up in n, and let's fix these parameters. So throughout the entire rest of the talk, we're always going to be interested in decoding to sort of optimally high noise tolerance to half minus epsilon. And we'll want the list size to be polynomial in 1 over epsilon, or at least some function of epsilon. We don't want it to scale with n. And the question is sort of if I want to get this all the way down to O of n, how many queries do I have to make? We said earlier that Katz-Trevisan says that Q's are going to have to be at least log n, but it turns out there's a massive gap in what is known in lower bounds and upper bounds currently. So I'll briefly overview this once I remember what board I said I was going to do it on.
Mention where the quantifier I comes in here.
So yeah, we can do this. There exists J in L such that for all I, the probability that the jth decoder computes F is greater than or equal to 3/4. That's supposed to be I. So there's one fixed guy in the list that on all indices locally computes F.
Is inside the locally decodable part.
That's where the quantifier comes.
Wait, sorry, did I do it wrong?
No, you did it right. I was just telling him,
Okay,
like, how he could have read it without you writing it.
it's fine. It's good to make it explicit. Thank you. It's somewhat of a weird notion. It's extremely useful. I think the first time I saw it, or like Swastik tried to explain this to me, I was very confused by the quantifiers as well. Okay, so, right, I was here. Let me tell you briefly, I'm going to give short shrift to a lot of papers, unfortunately. But let me tell you roughly sort of what is known in this higher rate regime. So for now, I'm just going to focus on the case where really like, I really want n prime to be O of n. It can depend on epsilon, but it shouldn't be, it should be a good code. Decodable from half minus epsilon and O of n, right? So what is known? I think, I don't actually know when this was, when Reed-Muller codes were introduced, but in the 60s. Okay, then for 50 years, for a long time, until about 2011, Reed-Muller codes, which are polynomial, based on evaluating the message as a multivariate polynomial, were the only example for the rate parameter settings of high rate codes that had non-trivial local decoding at all, not just local list decoding, but any sort of low noise local decoding. So until maybe 2010-ish, we had Reed-Muller codes. It's not particularly important what these are. I can tell people about it afterwards or if they want to ask. But these will have, roughly speaking, these will make for some alpha less than, or for any alpha less than 0, these will make n to the alpha queries and have n prime is some function of alpha, epsilon, and n. So I can't take alpha to be subconstant. Like, this is really something like alpha, 1 over alpha factorial times n. So if I were to take alpha to be subconstant, this would blow up massively. But at least these give me, sublinear time local decoding. It reads only a small polynomial fraction of the encode worth. I guess I should also say this is like also time. It's not just queries. It's an efficient sublinear time algorithm for local decoding. I guess the local list decoding was actually later, or maybe Aurora Sudan and Travis and Vidon gave high noise algorithms for this, which roughly can be taken to have the same parameters, I think, of half minus epsilon. So this is both low noise and high noise list decodable. Around like 2011 to 2015, there were a bunch of results that basically showed many new families of codes roughly achieved the same thing or with more flexible parameters or slightly better rates. But roughly speaking, there were a bunch of families of codes. In particular, the original one are what are called multiplicity codes, which take polynomials and their derivatives and have sort of somewhat better behavior. So this is still, it's still the same, but they're going to be an important player in the next year. Let me actually, these codes are due to a party. Start off funding and then list decoding separately. This is 2011. Sorry if I get the year slightly wrong. This is for low noise and Swastik showed also a list decoding algorithm. I think the next year, I don't totally remember. After this, there were a ton of other codes that were shown to satisfy this that I'm not going to go deeply into. Thing called lifted codes, expander codes in the low noise regime, tensor codes. But basically all of these were stuck in n to the alpha. There wasn't any known better than sublinear, right? We'd like, if my database is really massive, I really want to make like a sub-polynomial number of queries. I'd like it to be, smaller than any polynomial number. And this was finally achieved in, I guess, 2015. And this really nice paper of Koparty, Mer, Ronzavi, and Saraf. Already wrote some of their names. Saraf. And they realized that due to sort of the more flexible properties of multiplicity codes, what one can do is combine the multiplicity codes with expander-based amplification to reach to beat this Reed-Muller finally, to get a sub-polynomial time decoding algorithm. Sorry, this is a little messy. So they managed to achieve something like time n to the 1 over square root of log n. Right, so this is much smaller than n to the alpha for any constant alpha. The exponent is going to 0 with n. And n prime is constant, sum of. Okay. Unfortunately,
This doesn't depend on epsilon?
Yeah.
Okay.
I mean, okay, it does depend on epsilon, but here I really mean a fourth minus epsilon. Because it turns out these codes do not work in a high noise regime, at least as far as we know. These only have low noise decoders. And the reason for this, so multiplicity codes worked for high noise, algebraic things, we sort of know how to do high noise decoding. But once we try to amplify this with expander graphs, we don't know local algorithms for decoding, high noise algorithms for expander graphs. So this has been a barrier. And as far as I know, we've basically been stuck here since 2015, and we haven't been able to push either this further on the low noise side or to push high noise any better basically than Reed-Muller. That pretty much the state of the art is still just 1960s Reed-Muller.
Wait, but if it's below a quarter, then isn't it a unique decoding regime?
This is only the unique decoding regime. Yeah. So I'm saying there are not known codes in the list decoding regime that beat n to the alpha. This result only held in the low noise regime.
So it is unique decoding algorithm or?
This is a unique decoding algorithm.
Oh, both.
Yes.
Okay.
Yeah. This is unique decoding.
But you said you are going to fix the list size to be polynomial 1 over epsilon, so that's like list decoding things.
Okay, here O of 1 over epsilon includes 1. I mean, I'm overviewing here both the unique and the list decoding regime. Maybe I should have been more careful. Some of these, like expander codes, are only known to be uniquely decodable. So this is only, as far as I know, only unique coding. These are known, there are known algorithms for these in the high noise regime. Because this result combines multiplicity with expanders, you no longer get list decoding. You only get decoding up to the unique decoding regimes. Okay. Okay, so this brings us to finally. Should figure out some way to get to this earlier. Basically, can we fix this problem? Can we somehow upgrade the codes, the unique decoding codes of KMRS to codes that work in the high noise regime, right? That minus epsilon. So, can we build list? I'm just going to call them LLDCs, locally list decodable codes, with rho equals half minus epsilon, and Q is n to the low of 1, or even matching n to the 1 over root log n of KMRS. Okay. Sorry.
Max, so can you set alpha to be like 1 over, square root log n and get something there like n prime is quasi-linear or?
Yeah, yes. You would get, so the best known in this regime for list decoding, right, would have been something like, I might be missing logs, but it'll probably be something like 2 to the root log n times n. Yeah, so we know sort of quasi-linear block length, but constant rates is sort of far from. At least it seems like both the algebraic techniques and the expander techniques don't clearly show how to get past this barrier, or combining them, which is what KMRS does. Okay. Let me. Okay, so let's say that we're interested, in particular in this question of not a bit doing better low noise decoding, but just trying to match KMRS in the high noise regime. Trying to build maybe some sort of amplification procedure that takes this uniquely decodable code and upgrades it to a locally list decodable code. I claim that to do this, we can actually sort of construct a slightly weaker object. That's called an approximate locally list decodable code. I guess I can actually just look at it down here. So here in local list decoding, we required that we output this, list of local algorithms, such that, for any f that was within the desired radius, I output a decoder that exactly computes f with 3/4 probability at every coordinate. I claim that if I already have a unique decoding algorithm, this is a stronger guarantee than I need. All I actually need is that this decoder will decode f on most I, on 99% of I. Why? Right? If I had such an object, I could just sort of feed it into this low noise unique decoding code of KMRS and get a fully decodable code. So it's enough to change this to what is called approximately locally list decodable, which will change its guarantee to being not for all I, but let's say that the probability over I, that the decoder and the decoder's internal randomness, if the decoder is correct, is at least 3/4 or 99%, whatever. It doesn't matter what constant you write there, something greater than 1/2. So maybe people already believe this, so I'll be quick. But the claim is that the composed code, if I take something like this that I call C-approx, so if I take the composition of C-approx and CKMRS, that this will be a locally list decodable code. Why? Right? Because just very briefly, I can sort of view this object in 3 layers. Right? The original message F sits here. It gets encoded into KMRS here, and then it gets encoded by C-approx here. Right? This is what I mean by the composition of the codes. And now I have some W input that's sitting here. I run my list decoder for C-approx. And this outputs some, or rather, maybe let's do it this way. I want to decode the ith bit of F down here. And I try to run my KMRS decoder, right? I have some unique decoder for KMRS. And it's going to tell me like, okay, tell me the value of the input word on these locations here. So I can compute these up to 99% accuracy by simulating them using the approximate decoder, right? I take the word W, and here I just run my decoder for the approximate code, or one of these guys was guaranteed to compute F in 99% of the places. So I'm going to run this decoder, and 99% of the time, I'm going to get the correct encoding of F on this bit I. But then the guarantee of this decoder, this is only 1% noise, right? So this decoder is then going to correctly output F of I for all I with 3/4 probability. Okay, nothing complicated going on here. It's enough to solve this slightly weaker problem of approximate decoding. And this is also standard literature. A lot of papers that sort of do list decoding upgrade a unique decoding algorithm by proving some type of approximate decoding on top of it.
So the query will multiply.
Yes, the queries will multiply. Good, I wasn't that careful. So Q prime will be like Q approx times Q KMRS. So, this was what, like N over. And so as long as this is also something like, much less than this, I'm still gonna get the same asymptotic query complexity. So we'll actually construct codes where this is polylog n. So it'll be much, much better than the barrier seems to be unique decoding, not approximate decoding. Yeah, Peter?
That was basically the same.
Yes. Yeah, queries multiply. It seems to be much easier to get low queries in the approximate regime than the unique regime, so this won't be a problem. I mean, okay, it's not so easy. We have to use high dimensional expanders, but you can do it. Okay, good. Now I can finally state a theorem about a new theorem about approximate locally decodable list decodable codes. So maybe I've lost track of where I'm supposed to write things. Okay, so here's the first theorem. For infinitely many and n, there exists codes, an explicit code, strongly explicit actually, I'm fine that it's an approximate locally list decodable code. Here, approximately, I'm just going to assume it's like 99% or some constant. You can actually amplify this really easily, which I'll talk about after the break. With the following parameters, n prime will be O epsilon of n. Sorry, so again, as before, I'm always interested, right, in this case that I'm decoding all the way up to 1/2. And my list size is just always going to be poly 1/epsilon when I'm talking about things. So these are fixed from earlier. And Q will be log n O epsilon of 1. Okay. So as an immediate corollary, you do exactly what I'd written here before. You compose this code with KMRS. You immediately get full locally list decodable codes. At whatever query bound above polylog n that we know the existence of unique decoders. So one way to view this theorem is up to the dependencies of epsilon, which are bad or exponential. As soon as you give me a better unique local decoder, this will automatically upgrade it to the list decoding regime up to polylog factor n. Yeah.
For instance, for infinite many, how dense are those?
Pretty dense. It's within, I think it's within n polylog n. Like the next guy is always within a polylog factor. And this is very annoying. And actually the KMRS codes are also only, I believe, for infinitely many n. And I cheated because when I composed things, I needed the message length to match up with the block length. And you can do this, but it's a little bit annoying.
Oh, but you need constant rate, so you
right. You can't. You can fold to make it work. You can't. You're right. You can't just repeat things because it won't get you constant. Yeah. This was deeply annoying. I mean, it's not that hard to deal with, but it would be great if we could have these for all n. But they're based on these constructions of high-dimensional expanders, and we don't have constructions for all n that work. I mean, even when you're using polynomials, right? You don't typically get things for exactly all message lengths. You need some power of a finite field or something like this.
But that's constantly dense.
Not if the field size is 2 to the root log n.
Okay.
Which is what you need for KMRS, right? So it's it becomes annoying. Okay, but good question. So okay, I mean I'll just write there exist LODCs with of n, and both queries and time is MDO of 1/square root log n. There's log logs that I'm ignoring, but so this is roughly the state of the art at the moment. If you could improve the unique decoding, you would immediately get improved list decoding here, but we don't know how to do this currently. Maybe actually let me also mention very briefly that I forgot that there's a nice tensor code construction that I slightly lied, that achieves n the 1 over log n, but the list size is super constant. So we're not focusing on that case. But this, if you have like n to the alpha, the list size is like x poly 1 over alpha, so it blows up massively. Okay, any questions about the theorem statement? Wow.
And Max, you said the best lower bound here is this cat script on.
Yeah, as far as I know, log n is this, so there's still a huge gap. Yeah, there's a giant gap. It's an extremely interesting problem. It's not one, it seems like, I mean, I don't know. It seems like these high dimensional expander techniques that we'll cover second half next week. The methods that we use are pretty tailored to approximate decoding. So it's not clear how you would use it to get to, to beat this to the root log n. Yeah.
Some approximate list decodable codes can be locally encoded. Can your codes be locally encoded?
Yeah, so this, I was gonna get to this, but it's now been so long. So the answer is yes. I'll just write it here. I mean, they're encodable in polylog.
Oh, that's cool.
Yeah, so in fact, what I'm about to say in a second is that these have low depth small circuits that decode and encode them, which then gives you hardness amplification.
Oh.
Not the low depth that you want. And I'm sorry, it's not AC0 or TC0, whatever. It's polylog depth. It's enough to, I'm about to say a second application of exactly this theorem, which is nice, I think, uses this. Then I'll talk a little bit about hardness amplification. Yikes. Okay, so I'm going to do this very briefly. There's a second application of these codes that I really like, which is that local decoding is not the only useful notion of efficient decoding of a code. And another quite reasonable thing I can ask for, actually, that to some extent came up, is the circuit complexity of the decoding. And maybe more practically, you can ask, can I decode the entire message in parallel? Right? If I have n or n log n processors, can I in log n time decode the message? Right? So it's a question, which I'll basically write quickly, which is list decoding in NC1, which is the circuit class of log n depth polynomial size, I guess log space uniform circuits.
The impedance is log of the code word length.
Yes. Yeah, log of the code word. I mean, we're also, I really mean good codes. So here I'm thinking of epsilon as constant and n prime as O of n, so there's no difference in whether I talk about the message length or the, right? So just very briefly, it's been known since 1974 that in the unique decoding regime, we have NC1, well, not NC1, we have log depth decoders. So this is due to Zyabov and Pinsker.
Why do you say not NC1, but log depth?
They were random.
Okay,
So it's not logs, there's what construction.
that's it, there's not explicit.
Yeah,
Okay.
right. So 95, they became explicit with expander codes and Sipser-Spielman. So then Sipser-Spielman made this explicit. And I don't think they actually claimed log space constructible, but you can make it log space uniform at NC1. So this is unique decoding. It's an NC1. As far as I know, in the high noise regime, things got completely stuck. These are codes based on expanders and propagation decoding, and we don't have any good codes with propagation decoding in the high noise regime. They're all basically algebraic methods, so things like Reed-Solomon and Reed-Muller. These use things like root finding and solving linear systems, and so they take a log squared depth. So it's been known since maybe, I think essentially since Madhu's decoder for Reed-Solomon codes, which is like 97 or something, that you can do list decoding in NC2. Well, then what does this refer to? The length of the index or the length of here I just mean globally. So I mean, I will tell you the local circuit parameters here, and then I just multiply it by n, right? Because I just run it in parallel for every index. That's how I'm gonna do this.
What is it, C2?
Right, thank you. This is log squared and depth. And polygon size. In fact, it's known how to get like some n polygon size circuits. So these are extremely efficient. It's outputting n things, so it should be at least size n. Up to a log factor we can get. I guess even the Reed-Solomon ones are probably, and the expander codes are definitely n polylog n. I'm not totally sure. Probably Reed-Solomon is, right? Yeah, Shashank's nodding, so we're gonna go with yes. So the algebraic code sort of gets stuck at this log squared n because they use root finding and solving linear systems. As we'll see, theorem 1 is based on a high noise propagation decoding algorithm, which is very easy to parallelize. I should pull this one down first. Wait. So I'll modify this slightly to say the decoding circuits are also of size. Not blue is not visible. What's visible? Red?
Yellow.
White. I'll just use white. I lost my original chalk. Okay, I'll use what I was. Okay. This is decodable by size polylog n. I'm ignoring epsilon. And depth. Polylog log. And circuits. The local decoders are this. So if I just run all the local decoders in parallel and take a majority log n times over them, I'm going to get a full parallel decoding. So this implies you know, good codes in NC1.
What's the input?
To
like one of the circuits.
The index.
yeah, the index, but here I mean global. I'm using these local circuits I'm just running them for every I in parallel.
But like the receive thing is in prime bits. Like where did it go?
There's like I have my original word.
Yeah.
I guess for every index.
I guess it just hard coded into the.
Yeah.
No, I just don't think about it.
I
mean, there is a received word that you're treating as an oracle. I'm just wondering where it went.
I mean, like this is global. Sorry, you mean for when I'm turning this into an NC1 decoder?
Yeah, I mean, like it takes a.
Right, it reads all of W.
Yeah.
There's no locality anymore. Like the Turing machine gets the entire input W. And then I guess for each I, I'm trying to output, you know, what do I think I is? Yeah. For every local decoder, I'm reading the input at I, it's making the queries to the particular places in the machine. Yeah. And it's outputting what it thinks f of I is.
I'm just confused why the size is less than the input length.
This size is for the local algorithm. It's not less than the input length of the local things is log n.
But it takes an oracle, which is of length n. So, right? Like, so is there an oracle circuit? This is an oracle circuit?
Yes, it has oracle access.
Got it, thank you.
I'm sorry. It has oracle access to W.
Thank you.
Yes. There's some circuit that's computing W. It's going to call this.
Log in bits and then outputs the opposite of.
Yes.
So it's not like your normal Boolean circuit.
No, sorry. Right, once I want to simulate this and I have the entire thing, it becomes a normal circuit.
I got it.
Sorry, thank you. Yes, it has oracle access. Okay, should we take a 5-minute break? Let's take a 5-minute break and take a 3-minute break. That'll turn into a 5-minute break.
But you composed with this other code, right? So how could you like more.
Right, this gives an approximate decoding in NC1, and then I encode it with Sipser-Spielmann. So there's an NC1 decoder of Sipser, unique
What do
decoder.
you mean list decoding in NC1? Don't you also need the decoding circuit of the other codes?
Right, so Sipser-Spielmann in the unique decoding regime, we have NC1 decoders using expanders. So this is like you put high dimensional expanders on top of expanders, and you get NC1 list decoding.
5 minutes.
Scatter.
Yeah.
So it was coming at some point. Okay. I'm so far behind that I don't know what's.
Yeah.
I guess maybe I will take a poll of the room. There are sort of two paths we could go from here. One of which is to talk about applications of this type of code and complexity and hardness amplification and pseudorandom generators. One of them is to actually construct a baby version of the code and talk about our propagation decoder. Either way, I guess maybe the following week, Yotam will cover the other part, so it doesn't super matter. Does anyone have a strong preference? They want to see the actual version of the construction of the decoder, or?
Oh, I want to see the construction.
Okay, everyone wants to see the construction, okay, we'll do it. Well, you can choose or not to cover the hardness amplification. Let me just mention briefly that the codes that we, so I will write this comparison, but I'll mention for the hardness amplification, we typically want to take epsilon as being really small with respect to the message length. And the parameters that we get in epsilon in these codes, that I wrote O epsilon, the parameters are exponential. So you can't take epsilon to be that small in these codes. So we have a second main theorem that gets polynomial dependence on epsilon, but has a log n, isn't constant rate, as an additional log n factor. So I was going to talk about those codes, and you can use these to construct linear time PRGs. I won't talk about this. I'll instead talk about sort of a baby version of our construction, and hopefully we'll see some short version of it next. Yeah.
It's different from the list size being poly 1 over epsilon that you're always taking.
List size is always going to be poly 1 over epsilon, largely just by like Johnson type considerate, because the rate's not going to be a capacity.
Okay.
It's going to be quite poor in comparison to capacity. This is non-trivial in the local model, right? Because I can't prove things, but it's still like, it's roughly for that reason. There's some cover of size whatever epsilon squared, so I just only do the cover. Okay, so Okay, so let me take the part of part 2, which was going to do what Rahul said, which was cover previous ALDCs, and then we'll actually look at our the baby version of the construction. Okay, so yeah, let's first say what was known before. So as far as I know, Avi can maybe correct me if this is wrong, the study of ALDCs arose in hardness amplification and cryptography and pseudorandomness, not in error correcting codes. So the first code corresponding, ALDC was actually Yao's XOR, basically, which can be was a hardness amplification result, but can be reinterpreted as an approximate local list decoding algorithm, basically for the complete hypergraph. So let me sort of say what the parameters of that code are. So that this had horrible list size, actually. It was a non-uniform argument. Later, Avi, Russell, Ragesh, and Valentin proved a polynomial 1 over epsilon list size version. So really the parameters are from IJKW. They're not from the original Yao lemma. But that was sort of the first code. Let me also say something briefly that Hanlin pointed out, which is part of the reason I introduced these codes as a relaxation, right? All we needed to do was approximately decode and then plug it into your unique decoder. But Hanlin was referencing, I think it was you, that these are locally encodable, that they have a stronger property. When I have a full error correcting code, every bit of the encoded message has to depend on many possible message bits, like a linear fraction of message bits. Otherwise, you won't be able to decode exactly. Approximate locally decodable codes, I can have local encoding, where to tell me what the ith encoded bit is, I only have to read like a polylog n or some very small fraction of message bits. Our codes do have this property. It turns out to be very important in hardness amplification. I won't be covering this side of things since we're going to focus more on the decoding side, but keep in mind that these are not just a weakening of LDCs. They really have this. So for instance, in this application to fast PRGs, this was going to critically use the fact that I could encode at least in some arbitrarily small polynomial time. Okay, so this is an important aspect, but not one that I'm going to highlight because we're missing the hardness amplification part. Maybe I should write back up our parameters. So our codes were n prime. So that's one of n, and q really the time or circuit size. Actually, upper bounds number of queries is like log n. 0.1. Okay, so previous codes were mostly actually in like the very low query regime. So they'll make a polynomial in one over epsilon many queries.
But epsilon is the 1/2 minus epsilon.
Yeah, 1/2 minus. The thing is in hardness amplification, the regime is different. Like I think of epsilon as really small, like sub constant with respect to the message length, like much smaller than 1 over log n, for instance. So in some sense, these like log n's really just become sort of polynomial in 1 over epsilon. But I guess maybe I'll ignore this for now. It's a different regime than encoding theory, where I usually think of epsilon as constant before. Right, okay, so the first such code is based on the direct product. I'll say what this is. On the complete hypergraph and choose R. So maybe I'll even mention briefly how this sort of relates to hardness amplification.
Briefly what hardness amplification is.
Yeah, sorry. So this is like I have a weakly hard function f, which means what? It means no, say, circuit of some size can compute f on more than 99% of its inputs, so an average case hard function. And I want to build from this a function that's extremely hard, that no circuit can compute on more than half plus epsilon, right? A Boolean function, basically where no circuit has has better than epsilon advantage on guessing.
Okay.
Right, then the idea is that you take really hard functions and you use them to build pseudorandomness, or you use them to build various things. So, and you can build them by just taking a slightly hard function, and it turns out encoding them with one of these codes will give you an extremely hard function basically immediately.
Cool.
Yeah, thank you. That's the one sentence descriptor of this. So let me say what it looks like here. All right, so the message will sit down here on message bits will sit here. Up here we're gonna have n choose R. Right, so each of these is an R set, and it's just this is a graph of degree R where I'm connected to the vertices that's a set. Right, this basically is a graphical view of the complete hypergraph. Right, all possible R sets of n. The point from hardness amplification would have been I start with this function f down here that's slightly hard, and I take the direct product encoding. Right, so I'm gonna encode this up here into encaf, and all I'm gonna do is at this set S, which is like V1 through VR, I'm just gonna aggregate the values of f. I'm basically just repeating the function R times. This was the core of Yao's XOR lemma. He would then XOR these to get a Boolean function, but we're just going to work on this sort of high alphabet case. All right, so encaf evaluated at S is just f restricted to S, right? Or S is this is some set of vertices. This is called a direct product code. Sometimes it's also called ABNR, or it's a version of AEL. These are versions of it in the coding theory literature. But so I could do this for any graph, right? I picked the graph here that corresponds to the complete hypergraph, but this could have been any bipartite graph, and I can always just aggregate the symbols along the edges of here. This is called a direct product encoding. All of our codes will be direct products Also note, this is locally encodable, right? To compute the guy here, I only make R queries down here. This is a little bit confusing and I apologize for this. Because this is in the high alphabet regime, the amount of noise that we can decode from is no longer half minus epsilon, right? That was for Boolean functions. Our goal is now to be decode all the way up to 1 minus epsilon fraction of errors. So a fraction of these big alphabet symbols being corrupted. If I wanted to move back to the Boolean case, which you need to for certain applications, I just take this and I encode it with an inner error correcting code, like the half-R code, to move back to the binary setting, and that'll move me from 1 minus epsilon back to half minus epsilon. I'm just going to focus on this large alphabet case. You'll have to trust me that you can just plug in a binary code to the large alphabet to move to the binary setting. There are some details here.
What should we think of R as, like polynomial?
Good. R, in this case, is just going to be O of log 1 over epsilon.
Oh, okay.
Yeah. Right. So basically, Yao's lemma was the statement that the XOR of this was an approximate locally list decodable code, albeit with massive list size. Avi et al.'s work showed that this is an approximate locally list decodable code with polynomial 1 over epsilon list size. So what are the parameters of this code? The number of R sets, right, is like roughly n to the R, so it's n to the O of log 1 over epsilon. So the rate is bad. Often we think of epsilon. Anyway, epsilon is small with respect to n, so this is a super constant. I mean, even if epsilon was a constant, this would be a polynomial rate code, and we think of it as even subconstant. This is, it turns out, decodable. I'll roughly give you the algorithm. Q will be poly 1 over epsilon. And okay, it's also doable by low depth, low size circuits, but I'm not going to say exactly what all the circuit complexities, etc. are. I'll show you the decoding algorithm for this in the next one in just a second, but first I want to mention, so this is sort of the original ALDC as far as I know. Then again, this paper, I should maybe write. Okay. So both of these constructions, the uniform versions are from this paper. Maybe the journal version is okay, I don't remember. So they gave both the uniform decoder for the above that has the small list size, and they give a very nice de-randomization of this using subspaces, using a different direct product. They said, right, maybe I don't have to take all possible sets, I can take some sparser system. And in particular, the construction, which our baby version will be very much inspired from, is taking vertices to be, I mean, again, this is n, but I'm going to view this as elements of a vector space, fq to the m. Think of q as being polynomial in 1 over epsilon. And I'm going to take here, instead of all possible subsets, I'm just going to take the set of 8-dimensional subspaces. And so this will be, maybe it's 5, some constant. I don't quite remember what constant you need. Of fq to the m, right? So there are roughly like n to the 8th of these, or something like this. Should I pick 8 basis vectors?
It's maybe called QP or something because it's not the.
Yeah, you're right. Okay, I'm gonna keep writing here, and you're gonna have to correct me. Okay, right, and this has degree something like p to the 8 or something like this. So it's actually the alphabet is much larger than up here. Right, up here it was log 1 over epsilon. Down here it's polynomial in 1 over epsilon. There are some tricks that you can use to reduce the locality. They screw with the rate slightly, but I'm not going to deeply go into this. So this gets you, this improves you to some polynomial rates. N to the 8th, and number of queries is like some polynomial on 1 over epsilon. List size and row are also, I guess 1 minus epsilon and polynomial on 1 over epsilon. I guess maybe I should also note I mean, you and Russell had a variety of other non-uniform constructions, right? Like using expander walks plus the Nason-Wigderson generator.
I don't remember now, but
There are some other constructions that also get this type of parameters that were used to de-randomize BPP under certain complexity assumptions. These are non-uniform. They had very large list size. They still had, as far as I know, polynomial blow up. I don't think it was known how to get even quasi-linear walk length here. I'm not going to talk about them due to time. This was, as far as I know, this was sort of the state of the art in terms of these codes. You had some polynomial blow up. Okay, I can actually just tell you directly what our code is based on this.
What is the encoding function for this?
Oh, it's the direct product code, right? So the F sits on here, and I just record the bit that I see on all of the vectors in my subspace. So this is also, yeah, every construction we're going to use is going to take some bipartite graph and take the direct product encoding. That's always, right, this is always some version of locally encodable. We'll prove that it's decodable. Okay, so a real construction is some sort of direct product over a high-dimensional expander. I very clearly cannot tell you what this is, and Yotam will talk about it next week. But here is a very basic version. Our goal is to get this n to the 8 lower. So I'm not going to get you to linear or constant, but I'm going to get you to n prime, which is roughly 2 to the square root log n. I could be more careful with the epsilon dependence. Yeah, sorry. That would be really small. N times 2 to the square root log n. So we'll get to quasi with a very simple modification of this that is going to lead to a bunch of technical difficulties over what the original decoder for this object was. So what will we do? We'll take sort of a large ambient vectors, okay, P, Fp to the 2D. What I'm going to do is take 2 central layers of subspaces that are right next to each other, instead of taking points and 8-dimensional subspaces. Right, so the layer here is going to be d-1 dimensional subspaces. So this is where the messages sit. And here is going to be d+1 dimensional subspaces. Right, and again, I draw edges by inclusion. So every d+1 dimensional subspace V is connected to all of the W that sit inside. Okay, so one thing to notice is that this is actually a balanced graph, right? By duality, the number of d-1 and d+1 subspaces are the same. So the only blow up in block length is from this alphabet, right? Every guy here is actually encoding a bit for every subspace that sits below it. How many subspaces sit in a d+1, how many d-1 dimensional subspaces are there of a d+1 dimensional subspace? It's something like p to the 2d up to some factors, roughly something like this. What's the total size, right? What is n? The number of d-1 dimensional subspaces. This is roughly p to the d squared. Right, so this is where this root log n comes from. N is p to the d squared. Okay, p is probably 1 over epsilon. I could be more careful. And actually, when epsilon is really small, you get pretty good rate using this. You can use it to build PRGs directly. But roughly speaking, d is about square root log n. Right, so this number of things is roughly 2 to the root log n. So you're going to get this total block, expanded block length of n times 2 to the root log n. Does that make sense?
This is not what you do in the end, but this is
some. This is the baby construction. I mean, this is like. Okay, I don't know how much I want to say about this.
That's fine.
Yeah, you in some sense replace this with a high dimensional expander. That will get you polylog rates, and then you replace it with some much more complicated encoding on a much high dimensional expander, and that gets you constant rates with a different algorithm. Okay. But this is enough, like, if I want to build, so one application of this is to build from some cryptographic and complexity assumptions to build linear time PRGs with nearly optimal seed length, outputting, T bits against size T. That you can just use this, because really there's going to be a log 1 over epsilon here. So if I think of epsilon as being even inverse linearly small and or polynomially small in n, I'm still going to get something like n prime is like n to the 1 plus alpha for any alpha going to 0, and I can use this to build a very fast PRG or something. So even this sort of baby version is, I think, a pretty interesting and useful object. But yeah, it doesn't achieve any of the coding results I said you can't do like this. But it'll set up also sort of the challenges that we need to solve. And 0.5, yeah, I could probably talk about them a little bit. Okay, any questions on the construction itself? I haven't told you at all how algorithmically we're going to actually list decode this object. Okay. So let me very briefly, Amit's mentioned that unique decoding in the approximate decoding regime is really easy on direct product codes. In particular, anytime you have an encoding on something that's called a sampler graph, which I'll define, you automatically get codes in the unique decoding regime. And then I'm going to try to give some intuition for where this fails at list decoding, and then sort of what the key idea is to move to list decoding even in these prior works. And then we'll see sort of why things get harder over here and how we deal with them. Definition. I think this is like maybe the last definition in the talk. So G is called an alpha beta sampler. I'm maybe just even going to draw, I'm just going to draw a picture, I think, instead of writing the probability. I'm not sure. No, I'll write the probability. If for all subsets A on L, so for every subset that's hitting here, the probability that when I pick a random vertex in R and I look at what fraction of its neighbors go into this set A, the fraction should not be more than alpha off from the measure of A itself on more than a beta fraction of guys down here. So almost every vertex sees A in the right proportion. This is called a sampler graph. So the formal guarantee, right, is the probability over a vertex from R that the expectation, maybe I'd say the probability over guys in L that are neighboring R of hitting A minus the global probability, right? Just the probability over L of A. If this is greater than alpha, should be less than beta. Again, just look at the picture, right? The probability that I sample this in the right proportion should be 1 minus beta. Almost all vertices see this in the correct proportion. I claim that it basically immediately gives a unique approximate decoding algorithm for the direct product code on here.
For small enough alpha and beta.
Right. Yeah. I guess if I take alpha to be epsilon over 2 and beta to be delta over 2 or something like this, right? The point is what? I have an input word W on here that's supposed to be on a half plus epsilon fraction of up here. This agrees with F. Right, so A is some set where I have the correct encoding of F. It's bigger than half by a factor of epsilon. What does sampling promise me? It says, for a random guy here, for all but a beta fraction, for all but about 1 minus delta fraction of guys down here, more than half of its edges are going to be into the correct set. So I can just decode by taking a majority. Right, and I'm only going to fail if I want to use less queries. I could subsample or something like this, but I'm only going to fail on this small beta fraction of guys that missample A. right? So this will give me a unique decoding algorithm up to half minus epsilon noise. But this is the high alphabet regime, so my goal is to get to 1 minus epsilon, right, in the list decoding regime. Okay, so why do things fail in list decoding? Like, let's say we only had half agreement. Now I could have two functions up here. I could have that on the first half of these guys up here, I'm the encoding of some function f. And on the second half, I'm the encoding of f bar, for instance. Now I pick a random guy here. Doesn't matter how good of a sampler I am, right? It's like I'm just going to see half 0, half 1. It's basically completely useless information to try to take a majority. Okay, so sorry, I have no idea where I have my notes. Right, so what's the idea to fix this in list decoding? The idea is to pick some sort of, I guess what Avi called an anchor or some advice. To say, assume that on some S up here, I actually know that W of S, correctly computes F. How am I given this? I'm just going to pick a random thing and guess that it's true. And basically my list is going to be the output of a bunch of these guesses. So say I knew on S that the value was F. And let's say I'm in this very simplified scenario where really, like, truly half of it is F and half of it is F bar. And I want to build, this list decoding algorithm that sort of untangles F and F bar. So how can I decode, at index I, how can I decode the value of Fi? Let's say I is not in this set S, right? So S has some neighbors. This is the neighborhood of S down here, right? This is all the guys that are contained in S. I want to decode I. Well, here's a trick, right? If I can find some S prime that contains I and also has edges into this neighborhood of S, I can check, does W of S prime agree with W of S over here? Right? And if it does agree, in this idealized scenario, I know that the value of WS prime on I is actually F, not F bar. Of course, this isn't generically true because this could have been random noise or it could have been adversarial, but at least heuristically, there's this idea of, say I know the value on some set over here, try to find some intersecting set, and if it agrees, say that, okay, probably this is because most of the values are actually equal to F on this and just output F of I. This will be sort of the method of list decoding for all of these codes, some variant of this idea, which I'll try to formalize to some extent. Okay, so maybe let me say very briefly what the decoding algorithm would be for the complete complex. And then I'll jump to sort of how we would decode on this actual quasi-linear variant. I have the complete complex guy up here. So in order for this sort of decoding to work, we need at least one thing, right? I needed to actually be, for any I, or for most I needed to be able to find an S prime that actually intersected with this neighborhood down here. Otherwise it was hopeless. Or maybe I could have made some chain, but at least initially I just want to find some S that immediately intersect this. On the complete complex, this is of course true, right? Every, I have every possible R set. So we say, I'm given as some advice on a set S over here. I know that WS is equal to F. So if I want to decode I, what's the natural algorithm? I'm going to pick some S prime that has a random half, that includes I, and otherwise sort of has a random half of S. Right? So you can view this as sort of, there are over two sets sitting as a middle layer here, and I'm going to take this S prime, which has a random half of S plus I, and then I'm just going to check, does so maybe sort of algorithm sample S prime containing I I'm just gonna say that R/2 intersects S. And, test is WS equal to WS prime on their intersection. If it is, I'm just gonna output WS prime of I. Yes. Output WS prime of I. Else, I'm just going to keep retrying until I find such a set. Really, I'm going to try it about O of 1 over epsilon times or something like this. And if I don't find it, I'll output fail or 0 or something like this. So repeat. Okay, what's the rough intuition for why this decoder works? Also, I should say, what is the list that I'm outputting here? I'm going to do this for, so this is a decoding algorithm for a particular fixed piece of advice S, right? This is the algorithm dec S. By actual list decoding thing, right? We said we generate a set of local decoding algorithms. I'm just going to pick about 1 over epsilon random S and output the family of dec S for this. Right, so the actual algorithm just outputs dec of S for I don't know, about O of 1 over epsilon random.
Just because it's this, an epsilon function is good. So you know,
Right.
one of them.
Right, so we're guaranteed that there is some epsilon fraction up here. Right, our assumption is that W, the input word agrees with F, and at least an epsilon fraction of the time. So if I do this about O of 1 over epsilon times, indeed, I'm going to find some advice that does actually compute F. Right, I'm going to, at least one of these guys is going to have a starting point where WS is equal to F, and then I'm going to do this intersection test to decode. So for whichever of the decoders happen to be that guy who picked F, I don't know which one it is, but I know with high probability one of them hits this set that computes F. Then I need to argue that in that case, right, this intersection agreement decoder that I've told you actually works, which is not trivial to prove, but I'll give you some intuition for why it's the case, and then we'll move to the subspace wherever it sits. We'll move to the subspace version. Okay. So
The intuition for picking like a random path is to sort of spread out the possible choices of subsets you might make.
the reason to pick rather than picking,
I don't know.
Yeah.
The R minus one.
There are advantages to make it smaller, there are advantages.
Yeah.
More parameters, yeah, sometimes you pick, well,
Okay,
anyway, yeah.
yeah. So here's one reason that here's sort of the intuition I'm going to give. Think of S and S prime as being random. Or rather a random edge, right? This is a random pair of hyperedges that intersect in R/2. It's like I took a random walk from an R set down to an R/2 and back up to an R set. Right, and marginally when I run this procedure, these guys are roughly random, right? Because I've picked O of 1 epsilon random starting S. Each of these, if I'm trying to decode a random index I pick a random S prime and I, so these are pretty much random sets. The point is the following. What's the intersection of S intersect S prime? If I fix S prime, the intersection of these is a random R/2 elements of S prime, right? So, marginally, S prime intersect S is a random R/2 subset of S. And we'll think about this as sort of a local graph. In this case, it's like a complete local graph where this is all the vertices in S prime, and then these are all the possible intersections that I have. Right, so these are basically all the R/2 sets, and they're connected to all the guys that they're in. And the point is, this is an extremely good sampler graph. In particular, what's the idea? If if WS prime, let's say that WS prime was more than delta far or very far from the function f. Like WS failed to compute f on greater than 1% of inputs. We'll think of this as being pretty far. The point is that if I take a random R/2 subset, Chernoff tells me with extremely high probability, right? If R is like O of log 1 over epsilon, I'm going to catch this, right? I'm going to sample some guys that do not compute f, but then the intersection test is going to fail because S is, I'm conditioned basically on picking S that does compute f. And the probability this succeeds, we take it so high that this conditioning doesn't matter. It's an epsilon fraction conditioning. So this is basically why the argument works. I'm lying because things are not quite uniform and there's a lot of annoyance in making things exactly work out. But this is the intuition. Because of Chernoff, this local sampling, the probability that I match basically implies that I am at least 99% close to f. And so then if I decode a random guy from S prime, I'll win with 99% probability, right? I'll correctly decode 99% of it. That's sort of the rough idea. Okay, does that make some intuitive sense to people? So then I'll move to the subspace code. So I guess while I'm pulling down the board, let me mention, the algorithm is exactly the same for the derandomized, for the other IJKW subspace code. Right, I just take two subspaces that intersect in a 4-dimensional subspace. I check if they agree, and I output, the value of I if they agree, and otherwise retry a bunch of times. The point is that this local graph is no longer Chernoff, but it's basically like a subspace versus subspace graph. It's still an extremely good sampler graph. So the probability I miss things that don't compute f is really low, and exactly the same argument works. Good. So what about this code? Why didn't they just do this in the first place? Okay, maybe for that reason. But there's also another problem. Right? There's sort of a very immediate problem with moving from polynomial rate to near linear rate. And that's that the diameter of this graph is large. Right? So before up here, I could always very easily, for any S and any I could very easily find S prime that intersected S. As soon as I move to some sort of quasi-linear or lower degree thing, that's of course not going to be true for almost all I. You cannot find such an S, right? So I guess I already drew it over here, but so there's a natural solution to this, right? What should we do? We can't find, we have some advice S prime. We're going to still use this sort of propagation decoding algorithm. There's I want to decode. Somebody suggest a method for me to use S to decode I. Yeah, take a walk.
Super constant long walk.
Take a super constant length walk. Right, so in this case, it's going to be a walk of length about root log n, or length d. So before I was moving from either 8-dimensional subspaces to 4-dimensional subspaces to 8. Here, there's a reason I've left a middle layer here of d-dimensional subspaces. I'm going to walk between S prime, S and S prime that intersect on a d-dimensional subspace. Again, I won't go through the details, but if I look at this local graph again, right? If I look at a random S and S prime, and I look at all the possible intersections of S prime with S, this is again some sort of subspace versus subspace graph, and if I set the field to be large enough, it's an extremely good sampler. So we're again going to have this type of guarantee. And okay, I'm going to take I. I'm going to pick, I'll call it ST for some length of t that is going to be the length path. And I'll try to build a random path from S over to ST. Right? Okay, I'm just, there's some question of what the decoding algorithm should be here. Obviously, my goal is to propagate advice starting, I know the value of S at S. I want to end up identifying whether some ST is the correct value. This path is of length roughly root log n. This is starting to seem a little bit problematic. Because remember that only a tiny, tiny fraction of this graph actually computes f. And now I'm telling you, take a super constant length walk through this tiny fraction of the graph and somehow end up still decoding with high success. So this is a little bit of a tall task. It turns out you can do it. I think at some point, your Tom reminded me that we had a direct algorithm that did this, but there's a better way. The better way is due to a wonderful pair of people. Well, it's indirectly due to Shashank to some extent. It's something called the list recovery. It's a reduction to a setting where instead of having only an epsilon fraction of guys that compute f, we're going to be given a list of functions for every input here. So the list is about a size 1 over epsilon, and for almost all values, f is in that list. So originally, when we were doing this, we had some much more complicated reduction to this setting where you use sort of inner codes that inherently sit on this object from some other dimension of subspaces. But it turns out there's a beautiful old reduction from around 2002 in the coding theory literature that does exactly this type of reduction from list decoding to low noise list recovery. So let me actually write a little bit more formally this guarantee. So in general, let's say I have this sort of direct product SV, matching over here, and I want to go from the setting where I have only, an epsilon fraction, where I want to somehow reduce from having epsilon fraction agreement with F to having lists, let's say G1 through GL instead of a single function on each point, right? These lists are all possible labelings for the message down here. And I want the following guarantee, this called low noise list recovery. I want to somehow get to the fact that almost all, and think of this as like much better than a 1 minus 1 over polylog fraction. Basically, like so small that we can essentially ignore the fact that the tiny fraction of S that do not have F in their list. Almost all S and S. So we'll get to, instead of a single input word W, we're going to get this input list L of S, right, which consists of, for every S in here, a list of possible assignments, a list of possible functions, such that for almost all S, F restricted to S is in this list. Okay, it seems like there's some more hope when we have this, right? At least when now we're walking through this length root log n thing, if my path is random, then I'm pretty much always going to have F in the list at every point throughout this process.
You want to index the S sub S has nothing to do with it. S.
Oh, capital S and little, this is
S.
little s and, I guess, sorry, thank you. For every little s set, and here we have a small list of functions. So how do I reduce to this case? Well, because we're sort of in this version of the problem where I'm willing to lose polylog n factors in rate, there's an easy way to do this. As far as I know, if you need the constant rate setting, we don't know of any easy way to do this, and you need to use some sort of inherent local codes HDX structure to do it. But because we're willing to lose polylog n factors, what I can do is this nice trick where I just sort of slap a sampler graph on top of this picture. I take another layer of a direct product encoding. Right, so my encoding now, instead of just being the direct product of S, right, the message sits here. In the original encoding, I just recorded the bits of F that I saw in here. Now I'm doing this in 2 layers, right? First I encode to here. Now I take T and I put in all the sets of bits that were encoded here into a giant block. Sorry, you can't see. Right, but this is just recording the recorded value on all of its neighbors. Does that make sense for the this like sort of 2-layer direct product encoding? It's still a direct product encoding at the end. It's just it's done in this 2-layer fashion. What's the point? The point is that if this is a sampler graph for sufficiently good parameters, what do I want? I guess I want it to be an epsilon. If this is sort of an epsilon beta sampler, the point is, okay, now I have my starting word W. Right, this is the direct product code. So I'm going to show you that if I have an epsilon, if F agrees on an epsilon fraction with the word W, I can simulate lists on level S where almost all of the lists have F in it. How do I do it? This is a sampler graph. So with extremely, think of the failure probabilities being really, really small, like 1 over polylog n. So with extremely high probability, this, a set S in here will have at least an epsilon over 2 fraction of its neighbors into this good set, right? This is the set A from before in our old sampler definition, because I'm at least like an epsilon over this. So this should have been epsilon over 2 sampler. Almost all of the guys see at least an epsilon over 2 fraction of edges into here.
Are you describing the 2002 reduction?
This is the 2002 reduction, yeah. Or at least some version of it. I think this is basically exactly it. Right, so the point is, how do I generate a listed S that almost certainly contains F? I just take, L of S to be the 2 over epsilon most common elements among its neighbors, right? If I want to, I look at S, I look at the value of S recorded on all of its neighbors up here, and I just say L of S is the 2 over epsilon most common values given to S. Right, a random neighbor of S, it has some plausible value in here for S, and I just take the 2 over epsilon most common. Over T. And in being a sampler exactly guarantees me, right, there can only be 2 over epsilon functions that are an epsilon over 2 fraction of your neighbors, right? So anytime I do indeed have an epsilon over 2 fraction of functions that compute F, F will be in this list. And taking a sufficiently good sampler graph, like taking this beta to be 1 over polylog n, I get that with extremely high probability, basically all of the guys on S have F in their list. Okay, what have I lost in doing this? Well, I lose in the rate basically by a polynomial factor in beta. I need to set beta to be polylog n, so it's okay over here because I'm losing this 2 to the root log n anyway. But when we move to the constant rate setting, we can't afford this. We'll need some sort of different trick to do this. Okay, I'm basically out of time, so I think we'll need to do the propagation algorithm next week, but I'll give maybe a taste of the propagation algorithm and if that's okay. So, I mean, roughly speaking, the idea, I think at this point should be relatively clear. I am just going to do what I said, right? I'm going to take a random, or what Avi said, actually. I'm going to take a random path. I guess this was D+1 dimensional subspaces, and it's D-1. So my algorithm is going to be the following. I'm going to pick, some random V that I want to decode the value of F of V on. I'm going to pick a random, W up here. I guess I was calling them S prime that contains V. I've picked randomly, just like in the complete complex code, some S prime advice that I'm assuming. I guess now, like at this, I have a list, right? Each of these actually has, G1 through GL. One of which I'm basically guaranteed is F. So at this point, I've reduced the propagation problem to saying, say I know which G in this list is F, which I just do by guessing, right? I basically just output a decoder for each of these possible functions. One of them computes F. That's going to be the decoder that locally decodes F. And then I say, given that information, I want to identify which G in here computes F, or at least identify some G that is approximately close to F. Okay, so you can sort of imagine how this is going to work, right? I take this random path. On subspaces, this is quite easy. So in general, there's a major subtlety here, which is that I need to be able to compute a random path in the graph system I'm using from S to S prime in polylog n time, low depth circuits, etc. So it's some sort of strongly explicit pathing scheme that you need. This is highly non-trivial to do in general. In subspaces, it's really easy, right? I just take a random basis of S, a random basis of S prime, and I trade out the basis vectors between them. It's super easy to path. When you move on to bounded degree HDX, this becomes quite an interesting problem, how you can do this strongly explicitly. But let's say that we can, in fact, sort of sample a random path sufficiently random path from S to S prime. So what can I do, right? So I look at the list here. I look at the list here and I try to match the, I have some advice over here. I try to match the closest elements from this current list on the intersection between, S1 and S2 as I walk along. You have to be a little bit careful because remember that the decoding is approximate. Like we saw in the complete complex case, it could be when I move to S prime, there's some 0.05% that didn't agree with F, but I missed it because my sampling isn't strong enough. You have to be very careful that this error doesn't build up along a super constant length path. But there's a trick, which is not so hard that I can describe at least easily. I won't do the analysis, maybe what Tom will, which is to say at each level, like I just write the algorithm, it's quite easy. So I'm going to start with L1. At each Li, I'm going to have a list of candidate options that are going to be good. L1 is just going to start with the sort of G1, which I've assumed is F. This is the thing I've been given as advice that is F. At step I, I will set Li to be all functions in the list that exactly match any function in the previous list in the last step. So Li is, all G, and so we're now looking at Si versus Si minus 1 in this path. I'm saying Li is all G, such that the distance on the intersection between Si minus 1 and Si of G and Li minus 1 is 0. Right? And because in the list recovery setting, I'm guaranteed that all of these functions have F, this is a non-trivial algorithm because F is always going to appear in this list, right? It always has zero error. And you can prove pretty easily by this same type of sampling behavior, right? That when I pick something that has zero agreement on the intersection, I can't have moved too far from F. Because if this path is random, the probability that I miss, a large portion that's away from F is extremely small. I can take it to be small enough that I can assume it never happens in this path. So I just walk along this path and I end up with a guarantee that each time I basically build up linearly some small error term. So say if I set my sampling parameters to have sort of only delta additive error, at the end of the path, I pick any GT in this final list, right, that I've done through this process, I can guarantee that it will be sort of O of T delta close to F. And in particular, as long as I pick delta, which is basically some parameter, as long as I pick the field size to be much smaller than 1 over delta, I can guarantee this type of sampling. So I can set it to be like polylog n or something like this. I'll end up with the guarantee that the n function is like little o of 1 close to F. So just picking a random V out of that set, I'll almost always decode the correct bit, right? Except with 1 over polylog n probability or something like this. Okay, of course, there are details of various quantifiers and getting things to set up correctly, but this is roughly the algorithm. I pick a random S1, I output decoders for every function in its list, but I've done the Gershwaming and Dick reduction already. I have these simulated lists. And then each of these decoders just runs the random propagation algorithm where, to decode V, it picks a random S prime, it takes a random path to S prime that identifies some GT that's close to F, and then it just, output. Like I said, I output GT. That's the full algorithm.
And Max, with the properties of the slope subspaces that we're using here is that you can get this large intersection and that you can walk along these large intersections. Is that
good? Yeah, exactly. So the property that we're using here, yeah, there are two properties, right? One is that there is this path of intersecting sets. And so really sort of this, you can visualize this decoding process as I'm walking along this path of intersecting sets of vertices. And what are the guarantees that I really need about this path? A, that it's reasonably short. It should probably be like polylog length at most. And B, there should be this sampling guarantee that if I'm moving from a random S2 to S3, then the probability that this intersection for any function that's sitting in S3 the probability that the distance of f from this function looks very different on the intersection with S2 than it does on S3 is very small, but it should always sample correctly. So this is basically this local graph guarantee, right? Where we took S and we said, build the graph that's S, and then for each of these random neighbors S prime, I have a guy that is connected to the intersection of S with S prime. This is just saying this is a sampler graph. So that's basically the guarantee, that you have this system where there's this sort of decoding procedure where all the local graphs are samplers, and there is some sort of strongly explicit randomized scheme that given any S prime in this huge graph, in polylog n time or circuit size, routes, adapt away from S to S prime, which for subspaces was trivial because you just pick a basis and trade things out. It's also really important that this path is random, right? Because this sampling guarantee was only true for a random edge in this graph. It's not true for an adversary can always corrupt an arbitrary edge. So you really need some sufficiently random, strongly explicit pathing scheme plus local sampling. That will get you, we had these issues with polylog and rate blowup, et cetera, but if you're not worried about polylog and rate, that will give you a polylog and rate code. And polylog and quasi-linear block length code. I don't know any systems that do this at polylog and degree other than high dimensional expanders. There's this gets you 2 to the root log n because of subspace structure, right? How many subspaces sit in a d-dimensional subspace? I think it would be really interesting if there was some other type of structure that did this with quasi-linear rate. I don't know of any such structures. I've actually wondered for a while if there's some simple way to push beyond 2 to the root log n that doesn't require sort of polynomial machinery.
Okay, thanks, Professor Orr.